Many solar panels have already been installed in this school. A lot of effort has been put into the Solar Harvest Scheme.
EMSD introduced the Solar Harvest Scheme in 2019 to promote the local development of renewable energy. The solar energy generation system is equipped with a real-time monitoring system where real-time data can be obtained. The data includes solar irradiance, daily and monthly yield, total yield, and the amount of carbon reduction. The data can also be downloaded for educational purposes.
Dr. Tong, I've been to a participating school of the Solar Harvest Scheme. If we wish to improve the efficiency of solar panels, any special reason why they place the panels like that?
That is a good question. I'm going to conduct an experiment to study how the illuminance on a surface is affected by the incident angle of light. This is closely related to the output power of solar panels. If the illuminance is higher, the output power of the solar panels is higher. Here are two smartphones. One is used as a light source. Another one is used for receiving light. Here is a light meter. This arm can be rotated about the center. We can change the angle between the light meter and the light source. The angle of incidence is measured in this way. It is 0 degrees when light is incident normally. As it is rotated, the angle rotated is the angle of incidence. I will change the angle of incidence slowly and you can read the illuminance. Let's turn off the light. The angle of incidence is 0 degrees now. Look at the reading of illuminance.
It's 456 lux.
Let's increase the angle. It is 20 degrees now.
It's 432 lux.
The angle is increased to 40 degrees now.
It's dropped to 327 lux.
As the angle of incidence increases, what happens to the illuminance?
It decreases gradually.
That is right. When light is not incident normally but obliquely, the illuminance of the surface decreases. The same amount of light energy is distributed to a larger area, as shown in this figure. The light energy distributed to a unit area decreases. That is why it becomes dimmer. This is closely related to the efficiency of solar panels. When light is incident obliquely, the output power is lower. Thus, we try our best to orient the solar panels normal to sunlight and achieve optimal performance.
That means we make them face towards the sun for the highest efficiency.
Exactly.
In the previous experiment, the illuminance was highest when light was incident normally. It was lower as the angle increased. How does it affect the output power of solar panels?
Let me give you a hint. The solar panels face towards the sky. The orientation is fixed. The sun rises in the east, reaches the highest position in the sky at noon, and sets in the west in the evening.
At sunrise and sunset, the angle of incidence is the largest. Less light is received. In contrast, at noon, the sun is right above the solar panels. More electricity could be generated at that time.
That's right. This phenomenon can be verified using the RTMS data of the Solar Harvest Scheme. Let's look at it and see if it agrees with our expectations. The data is here. It shows the data of a sunny day in a school. Time is on the x-axis. It shows the local time of the day. There are two y-axes. The orange curve shows the solar irradiance. It measures the amount of sunlight received by the solar panels. The scale is shown by the axis on the right. The unit is watt per meter squared. The blue curve is the output power of the solar panels. The scale is shown by the axis on the left. The unit is kilowatt. In the beginning, at about 6 a.m., both curves start increasing. That means the sun rose and there was sunlight. At noon, about 12 o'clock, the sun was right above. Sunlight was the most intense. The output power was thus maximum. At about 6 p.m., the sun set and the readings became 0.
Why is the orange curve smoother while the blue curve jumps at discrete levels?
It is the data on a sunny day. The sunlight was stable. That is why it is smooth. The blue curve, showing the output power, is the average value of each 15-minute interval. It thus appears discrete.
According to the graph, if I adjust the orientation of the solar panels every few hours, the solar panels can receive more sunlight during the day and generate electricity all day long.
That is a smart idea, but it is not done by hand. There are some advanced solar panels capable of tracking the sun automatically. They can face the sun all the time and receive more sunlight to generate more electricity.
That sounds interesting, like a sunflower.
Exactly.
An hour in the morning is worth 2 in the evening. We are the most energetic in the morning, but it is not applicable to solar panels.
Solar panels generate the most electricity at noon because sunlight is the strongest at that time.
They have the best performance at noon. Solar panels absorb sunlight. On cloudy days, they can't generate electricity, can they?
That is not totally true. Solar panels also work on cloudy days. On cloudy days, even sunlight does not shine directly on solar panels. Some sunlight can still be scattered by the clouds and molecules in the atmosphere. The indirect light can reach the solar panels. This indirect sunlight is indeed weaker than direct sunlight, but it is still effective for the solar panels to generate electricity. Let's look at the RTMS data. We can compare the output power of the solar panels on a sunny day and a cloudy day.
Does it really generate electricity on cloudy days?
Here are two curves, which represents a sunny day, which represents a cloudy day.
The smooth one represents a sunny day. The other one is irregular.
Correct. The smooth one represents a sunny day. This graph shows the solar irradiance. The unit is watts per meter squared. The smooth curve is higher because sunlight is more intense on a sunny day. The solar irradiance is higher. There was no cloud on that day. The change in the incident angle of sunlight was smooth. This gives a smooth curve. It is different on a cloudy day. The curve is lower because the clouds blocked some of the sunlight. Only indirect sunlight could reach the solar panels. The solar irradiance decreased. There is another issue. You see the fluctuations on the graph. The fluctuation was due to the clouds. When a cloud passed by and blocked the sunlight, the solar irradiance suddenly dropped. When the cloud left, the sunlight was no longer blocked, the solar irradiance rose. As a result, the curve is irregular. Let's look at the other graph. It shows the output power of the solar panels. The unit is kilowatts. It is simple. The output power on a sunny day was higher than that on a cloudy day. When we carry out this experiment, we need to ensure a fair test. The two selected days, the sunny day and the cloudy day, should be close to each other. The effect of seasonal change is minimized. We want to compare the effect of weather on the performance of solar panels only. How do we know the amount of cloud on those days? We refer to the cloud amount data from the Hong Kong Observatory. The power output on a cloudy day is lower, but electricity is still generated. Solar panels are not useless even on cloudy days.
The effect of weather is significant. There are many cloudy and rainy days in Hong Kong.
Here is the data showing the output power of solar panels in Hong Kong within a year. We have put in some effort here. We obtained the monthly cloud amount data for a year from the Hong Kong Observatory. The graph clearly shows the variations. In the months with a higher amount of cloud, the output power of the solar panels was lower. In the months with a lower amount of cloud, the output power of solar panels was higher.
I see. I didn't know that electricity can be generated even on cloudy days.
You should learn from the solar panels and work hard the whole year round to perform well.
Got it. I'm going to study now. Dr. Tong, we have mentioned that the incident angle of sunlight affects the output power of solar panels. Is there any difference among different regions or countries?
Of course. The effect mainly arises from the latitude. If we are on the equator, the sunlight shines almost directly overhead most of the time in a year. the output power of solar panels is higher. If we are far in the north or in the south, like near the North or South Poles, sunlight is mostly oblique throughout the year. In those places, the output power of solar panels is much lower. Another important factor is the seasonal changes. Even in the same place, the position of the sun in the sky changes in different seasons. This also affects the output power of solar panels.
What about Hong Kong? How do the seasonal changes affect the output power of solar panels in Hong Kong?
Let's look at the computer simulation. This is the Earth and this is the Sun. It is not drawn to scale. The Earth revolves around the Sun. The axis of rotation of the Earth is not perpendicular to the orbital plane. It is tilted by 23.5 degrees. This tilting angle doesn't change when the Earth is revolving around the Sun. In the middle of spring and autumn, the vernal equinox and the autumnal equinox, sunlight is incident directly on the equator. The equator receives the most sunlight. For summer, in the northern hemisphere, which is about the end of June, the northern hemisphere lies towards the sun. More sunlight reaches the northern hemisphere. Sunlight is incident normally on the Tropic of Cancer. For winter, in the northern hemisphere, which is about the end of December, sunlight is incident normally on the Tropic of Capricorn. The northern hemisphere receives less sunlight. These factors affect the amount of sunlight received in Hong Kong in different seasons of the year. Let's look at another computer simulation. The simulation shows the sun paths in the sky observed in Hong Kong in different seasons.
Dr. Tong, the sun always rises in the east and sets in the west. How come there's any difference?
It is not that simple. In the northern hemisphere, such as in Hong Kong, the sun rises in the east and sets in the west only on vernal and autumnal equinoxes, the middle of spring and autumn. In the middle of summer, the summer solstice, the sun does not rise in the east but in the northeast and sets in the northwest. In the middle of winter, the winter solstice, the sun rises in the southeast. It reaches the highest position in the sky and sets in the southwest. The paths show that in summer, the sun is high in the sky at noon. Sunlight is almost normally incident. At that time, the output power of solar panels is the highest. But in winter, the sun is at a lower position. Sunlight is oblique. The output power of solar panels decreases. In between are spring and autumn.
The sun path is longer in summer than in winter.
As everyone knows, summer has longer daytime and shorter nighttime, while winter has shorter daytime but longer nighttime. Apart from direct sunshine in summer, the other factor that affects the performance of solar panels is the sunshine duration. Sunshine duration is longer in summer and thus more electricity is generated.
We have talked about the incident angle of sunlight, but how should we place the solar panels so that they face towards the sun at the best angle and absorb sunlight most effectively?
It is clearly shown in the simulation. In the northern hemisphere, such as in Hong Kong, the sun lies in the southern sky at noon. The angle of elevation depends on the season. When we place the solar panels, they are not laid flat on the ground, but inclined to face southward. When the sun reaches the highest position in the sky, sunlight is directly incident on the solar panels. The efficiency of electricity generation is thus higher.
Can we see the seasonal variation from the data?
Of course. This is the data obtained from the school. We have selected 2 days. One is near the summer solstice, another is near the winter solstice. For a fair test, the cloud amounts of the 2 days should be similar. The cloud amounts on both days were about 60%. We see these two curves showing the solar irradiance on a summer day and a winter day. You can see the fluctuations. It is because both days were cloudy. When a cloud passed by, the solar irradiance dropped suddenly. The solar irradiance rose when the cloud left. Despite the fluctuations, you can clearly see that the curve of summer is generally higher than that of winter.
Yes, the sunshine duration is also longer. In summer, the sun rises earlier and sets later.
The output power of solar panels also shows this trend. The curve of summer is higher than that of winter. The sunshine duration is also longer in summer.
Human beings should adapt to nature and use the resources properly. This is good for our well-being.
You have gained some new insights. Work harder. Your future is bright.
It is vital to use natural resources properly. In the past century, humans relied too much on fossil fuels. Along with deforestation, the amount of greenhouse gases in the atmosphere has increased. This results in an increase in global temperature. Hong Kong is facing more frequent extreme weather events. In 2017 and 2018, Hong Kong was severely hit by super typhoons Hato and Mangkhut respectively. They caused extensive devastation. If we're still reluctant to make any changes, climate change will pose bigger threats to us. To cope with climate change, we must take prompt actions to reduce carbon emissions and achieve carbon neutrality.
Yes. In 2021, the Hong Kong SAR government announced Hong Kong's Climate Action Plan 2050. A series of strategies and targets were set with a view to achieving carbon neutrality before 2050. The government has been taking the lead in developing renewable energy, including raising the requirements of applying renewable energy technologies in government buildings and developing renewable energy projects of different scales in suitable premises.
Everyone has put in a lot of effort. We need to keep working together to achieve carbon neutrality before 2050.